So what we are going to be learning about is finding the confidence intervals and the hypothesis test for a difference of proportions. And there is some nuance that we're not necessarily going to be covering today, but knowing what we talked about a second ago with the review of our combination of random variables, and when we're talking about standard deviation, it's the combined variance. All right, so let's remember, what's a variance of a single proportion? The standard deviation, and here I'm going to pull this straight from right here on the formula sheet. So if I look at that, the standard deviation, and you'll recognize this formula, is square root of p times 1 minus p all over n. So if this is the standard deviation, then the variance, which is the standard deviation squared, is going to be the same thing, p times 1 minus p all over n. It's just that. You get rid of the square root. And I show you that because let's look at the standard deviation real quick. Maybe I should have started with the mean, but I'll come back to that. So the standard deviation for a sampling distribution of difference of proportions is going to be, this p sub 1 is the hypothesized proportion. Or, well, no, it's actually going to end up being your p hat, I'm sorry. But anyways, but notice it's p times 1 minus p sub 1 times 1 minus p sub 1 all over n sub 1 plus p sub 2 times 1 minus p sub 2 all over n sub 2. This is the variance of p sub 1, and this is the variance of p sub 2 of our first random variable. I maybe shouldn't call it p sub 1 and p sub 2. So we're combining the variances together, and then we can take the square root of it, and that gives us a standard deviation. So what I hope to convey with this is that this is recycling an old concept, and we're just substituting in specific values for proportions. Okay? Same thing with this. One thing that we just learned on the previous page is that the mean of a random variable x plus or minus y equals the mean of x plus or minus the mean of y, depending on what it is we're doing. So in this case, since I'm subtracting, I'm going to subtract, and the mean, okay, and this is where I hope I don't lose you and confuse you with this. The mean of a sampling distribution of p hat sub 1 is going to be the same as a population proportion. So what we eventually get to is we just take p sub 1 minus p sub 2. We subtract those, and that gives us the mean of the sampling distribution. Was that helpful? Was that clear?
No, I'm sure we'll figure it out.
In practice, this will work out. Okay, I'm not sure if I explained it clearly, but we can come back to that, and maybe we can find a different way of saying it if it's not making sense. We do have a couple of things. The main takeaway from this is, I want you to notice, is that when we check our conditions, we need to check conditions for both samples. This is going to eventually be what we call a 2-sample z-interval and a 2-sample z-test for a difference of proportions. All right, so notice that you have to do n times p and n times 1 minus p for both samples. You have to check 10% for both samples. And we will run through the full process. And here's the conditions, and this is also from that worksheet, and it'll just be good to know. So here's what we can do. Check your large counts for both of these. And we're good. Okay. So let's see here. There is going to be a little bit of nuance when we get into the significance tests compared to the confidence intervals. So let's start with confidence intervals. And our point estimate, we are looking at a difference of proportions. So my statistic is going to be the difference between my two proportions, and it's going to be plus or minus. The Z star is still the same. This is a critical value based on whatever our significance or our confidence level is. And then we'll have to calculate this in our own special way. Now, okay, maybe I shouldn't jump too far ahead. Let's go back to this. I'm just using this as a blank screen. All right, so now let's pull these numbers back up. And we have two different samples going on. I've got those who are given the yawn seed and those who are not given the yawn seed. And then did they yawn, yes or no? All right. And I still, even though I'm going to rewrite it, I want you to have it on your own paper. So the yawn seed, sorry, I'm writing it wrong, was 4 and 12, which means a total of 16. And then it was 10 and 24 for a total of 34, which means we had 50 people total. 14 yawned out of the 50 and 36 did not. Okay. So I want you to have this written down because I want you to be able to refer back to this and see the process that you went through. The first thing we need to figure out is what's p hat sub 1, what's p hat sub 2, and maybe we can figure out what's 1 and 2 in this case. So this can be arbitrarily decided. And the yawn seed, let's say those that were given the yawn, we're going to call this, the proportion that we get out of this is p hat sub 1. And then this will be p hat sub 2. So when we're talking about 1 and 2 here, you can pick other things besides 1 and 2. But when we're saying 1 and 2, that's going to be the proportion of people who yawned, given that they had a yawn seed. So what is my proportion for 1, p hat? What fraction will this be? Wait, am I getting this? Oh, shoot. I'm getting this wrong. I mean, the numbers are all good. I just need to flip these two. Dang it. More people were given a yawn seed than were not. Okay.
So the group that got the yawn seed was the 34.
Yes. I mixed that up. I apologize. So only 16 people didn't get a yawn seed, and I apologize. So what proportion of people yawned, given that there was no yawn seed? I'll put the no here, and I'll erase this so it makes sense now.
Say that again?
What proportion of people who did not get a yawn seed, what proportion of them yawned?
A third.
Not a third. How many got no yawn seed total? 16. So it was 4 out of 16.
Oh.
There it is. No, you're good. So the p hat sub 1 is 25%. 25% of people who didn't get a yawn seed yawned. That's almost like a baseline we can compare it against. Now p hat sub 2. So 34 got the yawn seed. How many yawned? Ten of them yawned out of 34, so we can figure out this, and we'll just round it to the nearest hundredth. 0.29. So initial results is that there is some evidence that seeing someone else yawn is going to be, what's the word I'm looking for? contagious. There we go, contagious. Seeing someone yawn is somewhat contagious because there's a higher percent than people who didn't get yawn seed. Now, it doesn't look that big of a difference. Okay. So at this point, what we want to do is we want to lay out some hypotheses. And the hypothesis that we're going to always start with is that there is no difference between these two populations. All right. So my null hypothesis is that the true proportion of people who yawned, now I guess we're doing, I'm sorry. I wanted to do confidence intervals first because I can take the same data and come up with a confidence interval. We will do the null hypothesis in a second, but first let's come up with a confidence interval. And the way that we do confidence intervals is let's first check our conditions. All right, is it random? Is it 10%? And is it normal? Which in our cases, which are case with proportions, that means it doesn't meet the large counts condition. So first of all, we don't have a real setup. We didn't get to watch the video. Were these randomly, do you think this is a random selection? Let's assume so. We have no better knowledge. So, and notice I'm doing 2 check marks. So maybe off here I can say for P hat sub 1 and for P hat sub 2, I'm checking them both. So yes, they're both random. We're going to assume so. Are they both meeting the 10% condition?
For sure.
For sure. You know, 16 and 34 people, they're definitely less than 10% of the population. So normal, this is where we're going to run into some problems potentially. Well, almost certainly. So we've got n, but when we do this, it's n sub 1. Let me give myself some more space. I have to do n times p, but it's going to be n1 times p hat sub 1. And then n1 times 1 minus p hat sub 1. So we have to do both of those calculations. But then I also have to do the same calculations for my second sample, which is we're considering our 2 samples to be the people who got the yawn seed and the people who didn't get the yawn seed. Every time I say the yawn seed, in my head, it somehow turns into like Beyonce. I don't know. I just keep, that's my world right now.
I'm sure there's like some Norwegian name. Jansi.
Yeah. Luckily, we're going to move on to other scenarios where we don't have to say this phrase over and over again. All right, so you can figure out real quick. We know what p hat sub 1 is. We know what p hat sub 2 is. We know what sample size, this I'll tell you is n sub 1. This is n sub 2. Now we already know what these numbers are going to come out to, because it's these same numbers right here in our two-way table. All right, but we can go ahead and do the math if you want to, just to be confirm. All right, so when you multiply that out, were you able to see it's 4, 12, 10, and 24? Okay, I'll pause right there to make sure that I'm not losing anyone. Now imagine they just give you the decimal and they don't give you a two-way table. Then at that point, you can multiply it out. So in our particular situation, we did not meet the large counts condition for the first sample, but we did for the second. And so knowing this and remembering back to what we said about this, what can we do if we don't meet this condition?
We could say that there may be error with our results, but that we're going to go ahead and run it.
Perfect. There you go. If you didn't hear, just say that there might be errors in our final analysis, but we're just going to keep doing it anyway, knowing that we didn't meet the conditions. Okay, so we checked our conditions for confidence intervals, and now I'll go ahead and say, yeah, we met for the second, we missed it for the first. So I will stop there. Is everyone good? Does anyone have questions? Okay, I'm not just going to clear the screen. I want to have some room. I will probably get rid of this two-way table. Now at this point, we just need to know what our in and N1, N2, and sample sizes and stuff are. I'll clear this stuff too. All right. Let me give myself a little bit of space. Oh, sorry. N sub 1 is 16. N sub 2 is 34. Okay. So now that we're ready to do our confidence interval, this is going to be called a two-sample Z or a two proportion. So sample or two, I'll put this up above, two proportion. Z interval for, and this is where we're going to put P sub 1 minus P sub 2. And so it's a difference of proportions. All right, and what P sub 1 minus P sub 2 represents here, this is the true difference in the proportion of people who yawn when not given a yawn seed and when given one. And you might be asking, why do we care about the difference between these two? If there is no difference between them, if the difference is 0, well, then there's no connection between whether you see a yawn or not. Yawning is not contagious at that point. All this talk about yawnings make me want to yawn the whole time too. Okay. So let's remember our generic formula is this. Well, actually, let's also pick a confidence level. What's a good confidence level to go with? That would be like a significance level for a test. 95%. There we go. Okay. So the typical, it's basically the stat. The generic formula for this is stat plus or minus the critical value times the standard error. Okay, and specifically, and I want to remind you that's straight from the front right here. I know I show you this over and over again, but maybe someone needs to hear it. So that's right here. It's the second one. Confidence interval right here. Okay, so knowing that, I will figure out what my statistic is. My statistic is, since I'm estimating the true difference, I have to figure out the sample difference. So I'm going to have to do P hat sub 1 minus P hat sub 2. And luckily, I know those values. P hat sub 1 is 0.25. And P hat sub 2 is 0.29. Minus 0.29. So the difference between these two is negative 0.04. So my stat is right here, negative 0.04. And are we okay with this? We got it? So let me go ahead and show that, negative 0.04. Actually, I don't want to do that yet. I don't want to plug numbers in. You can go ahead and start it, but I want to do p hat sub 1 minus p hat sub 2. That's my statistic. Plus or minus a z star, which is my critical value. And now the standard error. This is where we come to that formula where the standard error is the combined variances of the standard errors of the other of our two samples. So it's going to be, the square root, and now I'm going to have a big formula under here. It's going to be p hat sub 1 times 1 minus p hat sub 1 divided by n sub 1 plus p hat sub 2 times 1 minus p hat sub 2 all over n sub 2. And it's not n squared, sorry, n sub 2. So we've done this enough that hopefully the standard deviation, standard error calculation for proportions is something that you recognize well enough. But now what we're going to do is combine two variances together under the same radical. All right. And now here's where I want to actually plug in values. We found p hat sub 1 minus p hat sub 2. This is where we plug in the negative 0.04. Plus or minus my z star. What is the z star if we're going with a confidence level of 95%? No 5.
What was it? I feel like it's like 0.256. Oh, for 95? For 95%, I'm checking out. Yeah, I think that's there's 1.96. Oh.
There it is, 1.96. And again, to find that, that's the very last row of table B, and I can't see 95%. I think it's somewhere over here. You'll see your 1.96. Okay, now we need to plug in the numbers for this fun stuff. P hat sub 1, I have this separately. That's 0.25 times 0.75. The sample size for this is 16 divided by 16 plus, now I'm doing 0.29 and 34 for the next part. So it's going to be 0.29 times 0.71, all divided by 34. And I would highly recommend not just plugging this all into your calculator at once, just do one part of it at a time. We can figure out what, first of all, the margin of error is. Remember, your margin of error is anything right of that plus or minus. So maybe calculate your margin of error first, and then you can add and subtract that from your statistic. So I'll just pause real quick. Everyone can kind of do that calculation.
Hey, I want some videos.
Okay.
How was your first view?
That's good to know. Now, I want to check both of these for P1, and I'll give myself a little bit of space, and for P2. Well, really, and here's where I want to clarify. P1 and P2, this is what I am predicting, or I'm trying to make an inference about from the samples. But now I need to check these samples if it's okay to run inference for them. Are they random?
We should assume that the 25,000 Americans still have contact behind them, but we don't actually know.
Exactly, yeah. We don't know. And Yeah, we can assume. So that's where I would write a sentence to the effect, we can assume it's random. 10%, that's a lot of respondents. Is it still less than 10% of the population? Yep. I think so. Yeah, out of Americans, I think it's safe to say more than 250,000 24-year-olds. So we're good there. And now, are they normal? And this is where we need to do n sub 1 times p hat sub 1. Now, you probably can already tell we're not going to have any issues with this. It just has to be greater than or equal to 10. Do we meet this condition? Now, I don't want you to do any shortcuts on the AP test, but actually put the numbers in, multiply it out, show that you get more than 10 successes and failures in both cases. But yes, we've met this. We're good to go. Create a 95% confidence interval. All right. So let me remind you, it's the stat plus or minus your critical value times your standard error. All right. So I'm going to see, maybe I'll let you guys figure out the specific formula. Don't worry about plugging numbers in, but what is our stat that we're going to use? And maybe you can just tell me if you want to write it on the screen, you can. What's the stat we're going to use to make an inference about P1 minus P2? Well, I know what you're getting at. First of all, we wouldn't write it that way because it's proportion. But again, just generically writing this, we don't actually know the true P1 and the true P2, but we do have samples, right?
You don't want the actual value right now?
We're making inferences about the true value, but all we have is P hat sub 1 and P hat sub 2.
Yeah.
All right, so P hat, so this is,
it should be negative. Right?
yes. Yeah, so we can actually plug this in. We know it's 0.849, and this is 0.881, and that equals negative 0.032. All right, so there's our statistic, and this is going to be a weird thing, and hopefully we get enough experience doing this that you get comfortable with it. But your statistic is not just one value; it's a difference of values. So my statistic is P hat sub 1 minus P hat sub 2, the full thing right there. And the critical value, because we're dealing with proportions, what kind of critical value are we using? We have two choices. There it is, the Z star. And now you know you're going to have to expect that eventually you're going to be using T star. And that's going to be fun. I'm getting excited. So now we can fill in this. So what goes under the radical here?
The standard deviation. Shall I tell you like all of the whole formula, all of it?
Sure, see if you can do it.
All right. P hat sub 1 times 1 minus P hat sub 1 all all over n1 plus, and then the same exact thing, but you replace the 1, 2.
That works. So here's one thing I want you to think about real quick. I've tried to make it clear, but I don't always make things clear, and I know that. So I've tried to make it clear that you can just take this generic equation right here at the top and substitute in using specific values. Do you understand how we're finding those values from this right here, from the AP formula sheet? Okay, I see a thumbs up online.
What do you mean by that?
So the fact that I know I'm looking at a difference of proportions, so I'm going to be looking at two populations, and notice right here, you're making an inference using p hats of 1 minus p hats of 2. It actually says it right here. And now I know I'm going to be using these formulas somewhere along the way. If they're asking for a standard error, notice this column right here is for standard error. So the standard error for a difference of proportions is found right here. And I can substitute that in where it says standard error. So if you're confident in how you're using this formula sheet, you don't have to have this stuff memorized. Every piece that we needed to know to do this little bit down here at the bottom, it was something that was referenced on this sheet.
So you want to get on the AP test?
You get this on the AP test.
Oh, really?
Yeah, that's why I keep, yeah, this actually is from the College Board. Yeah. They give it out for free. Huh, they could make money off of that.
Idiots.
Yeah, idiots. That would be great if you took the test and they're like, you pay your $94 and like, it's going to cost you $5 extra if you want the formula sheet. Okay. So there we go. If you have questions on that, that's a great thing to kind of go through, do some practice problems, and you can go back and say, here's how I set it up. Did I make a mistake? What's going on? And then I can look through it with you. But anyways, now we've got this formula plugged in. Luckily, with proportions, it's pretty straightforward. Now we don't need to calculate it. They already give it to us. This will be p hat sub 1, and this will be p hat sub 2. I did do things a little bit out of order. Maybe we should have clarified all of our statistics and everything right at the beginning. Now I can also see this is going to be in sub 1 right here, and that's going to be in sub 2. All right. So at this point, we can start plugging in. Now I can solve for p hat. Well, we already did that right here. So my statistic will be negative 0.032. And I will let you guys fill in the rest of that and do the calculation. See if you can come up with the confidence interval for this. So that is what I got. That's what I'm hearing a lot of people got. Actually, is that what you got? Okay.
I was getting that though. I just didn't finish it.
Okay. Leo was on his way to that answer. And of course, I'm sure a lot of you were getting that. But only one answer ended up on the screen. So just to make sure, if you did make a mistake, I'm just going to fill in the numbers real quick. 1.96. I'm not going to go through the entire calculation, but we've got, see, p hat sub 1 was 0.849. I've got it written down on a piece of paper right here. Just look at that. 0.151 divided by 12,460 plus, that's a 0, 0.881 times 0.119 times, or sorry, divided by 12,678. All right, there we are. And again, from there, it's just calculator work. I will say this, and I'll say it at the beginning, your calculator has a function on here. If you go all the way into your stat menu and you go over to tests. Because someone's going to figure this out eventually. I'm going to go ahead and tell you. There is a 2 prop Z interval B. It's option B right here. Your calculator can do all this work for you, but actually I don't encourage anyone to do that. This is good for checking your work. Okay. And if you go into this, you need to know your proportion, you need to know your sample size, your confidence level. And actually it's not even, see, it's complicated how you do this because I don't even use a calculator for this test. So I'm not exactly sure how to do this. I need to double check. Well, no, you put in X as the number of successes. So you'd have to multiply that out to get your successes, and then N is your sample size. Anyways, if you can figure that out and you want to check your work, that's a good idea. The reason I say don't just use the calculator is because all of this work right here and here, and even this right here, setting it up, all this fun stuff, you need to show all of it anyway. And it's not that big of a leap just to go ahead and do the calculation once you get to here. Okay? So I don't encourage you to become dependent on the calculator in that sense. But I did want to point it out, those tests do exist here, and someone will probably figure that out eventually, so I might as well let you know. Okay, so let me go ahead and clear all of this off the screen. All right, and I know today was a little bit bumpy as far as how I was rolling things out. We have another problem right here. I don't actually intend on going through this, but you can see it gives some proportions. You need to go through and figure out the standard error, create the confidence interval, state an appropriate conclusion. So actually, we never concluded the last one. I'll bring all this writing back up. No, I didn't want to do this. Okay. Let me do this. Now we can draw a conclusion. Based on this confidence interval, do we have strong evidence that girls are more likely than boys to complete high school?
Yes.
Why do we have strong evidence?
Because the confidence interval is always either P1 is always less than 0.
There you go.
P1 minus P2 is always.
Yeah, it's always less than 0. It does not contain, it does not contain 0. Those are both equally valid ways of saying it. Both answers are negative, which means that P sub 1 is less than P sub 2. So my conclusion, my actual written conclusion here might be because the confidence interval is entirely negative, and does not contain 0. We have convincing evidence that females graduate high school. Well, it says are more likely. I'll say graduate from high school at a higher rate.
Is that a real statistic?
Yes. So the book does generally use, in fact, it might completely use real data in all these questions. Graduate at a higher rate than males. So now that was true in October 2000. But that's the good thing about statistics is that things can change over time and you run into all kinds of what's the best kind of statistics to use based on this problem and tracking things through time. So that.
And in statistics, you always remember the wacky, goofy, zany scenarios.
Yeah.
All sorts of characters, people.
Stats is just wacky and zany and goofy. You've got it. It's bonkers. Okay. So that is what we're looking at today. So if you have questions on this, I'm more than happy to run through this next example, but I will not record this. So if you wanted to go through it, we can do that. If you're satisfied with your care, then here is your homework 7 through 13, odd in the book. Again, look through that. Make sure you understand those questions. If there's any of them you don't know, feel free to bring them into class and we can go through them. Have a wonderful day if you are good to go, and I'll see you tomorrow.